Okay, so at the end of the previous lecture, we finished up to section 10.6. Today we start with the section 10.7. As a reminder, what we did in the previous lecture, after introducing rotational variables, we looked at some of the uses of those variables that we used to look at with translational motion and applied them to rotational motion. So things like the kinetic energy of rotation. And then we developed something new. We called it the analog of mass. For translation motion, we called it inertia or moment of inertia, I. We discussed the parallel axis theorem, which is how to find the moment of inertia about an axis that is not at the center of something, if we already know what the moment of inertia at that point. And then at the very end, we discussed torque and how does it work with rotation. Now, as you may have already noticed, torque to rotation is what force is to linear or translational motion. Just like for translational motion, to get an acceleration to start moving from someplace to someplace else, we need a force. In rotational motion, to start an acceleration and start something rotating, we need a torque. Whenever we spoke about net external force, here we will speak about net torque. So we had, for translational motion, Newton's second law, which was F equals ma. Translating here, okay, we also will have a force, which we will call a torque. Now, we have already defined torque as R cross F, or otherwise known as F tangential R. And as we know that tangential acceleration is equal to alpha R, we can substitute that, and we end up with torque equals mr squared alpha. Now, mr squared, we have defined it beforehand to be our moment of inertia. So our torque is equal to I alpha, which makes sense because we said torque is the analog of force, I is the cousin of mass, and alpha is the cousin of acceleration A. So we have done one of our usual translations from one language to another. Torque net equals I alpha, F net for translation equals MA. So the best way to explain how torque works, I think, is through a sample problem, which is in your book, sample problem 10.09. Now, if you're into martial arts, Judo, karate, taekwondo, kung fu, etc., you would know about something called a hip throw, in which you hold someone and you flip him or her over your shoulder onto the floor. Now, to throw an 80-kilogram opponent with a basic judo hip throw, you intend to pull his uniform with a force F and a moment arm D1 equals 0.3 meters from a pivot point on your right hip. You want to rotate that person with an angular acceleration of about -6 radians per second square. So that is clockwise. You want to bring him forward at that rate. And you can assume, so we're not calculating the rotational inertia, we're just assume it's 15 kilograms meter squared. The question is, what must the magnitude of the force be if you throw that person? Now, there are two parts of the question. Okay. The first part, assume you bring your opponent close so that your centers of masses are actually at the same place. Now, if we do that, I am pulling this person with F down here. Moment arm is 0.3 meters. And the only force that is acting other than that is gravity downwards. Well, my torque is I alpha. I know what I is. I know what alpha is. I can calculate torque. Torque is also R cross F. And I know my moment arm is 0.3 meters. So I equate these two. I alpha equals R cross F. And I end up with a force of 300 newtons. So I need to put in a force of almost 30 kilograms equivalent of mass, 300 newtons, give or take, to flip an 80 kilogram person over my shoulder. But that positioning is very, very important and key to this judo flip. Because if you don't actually align the centers of masses together, you end up with a situation that is quite different. Are you seeing my screen, by the way?
Yes.
Okay. What happens if I don't align these two? Say, for example, if I am not an expert in judo or karate, and I don't know how to do it, and instead I try to pull this person over without bending him. So see here, he's bent exactly at the shape, centers of masses together. Here, that person is still standing up properly. And I'm trying to do the same thing, get them over my shoulder. Well, things are going to be quite different because now there's another moment arm between the two centers of masses. So now I have a more complicated situation. My torque is still equal to I alpha, just like my F net equals MA. Here my torque net is equal to I alpha. I still want the same alpha, but my R cross F is not only RF of my force, there's also another RF with respect to the second moment arm and to the gravity. So when we are rotating, we cannot rotate about two different axes. I either choose this or this. Now, if I choose this for rotation, I need to take this FG and multiply it by this distance perpendicularly to get torque. So I have minus D1F plus D2mg I alpha. And my force now is slightly more than doubled. I need 610 newtons. Yeah. Which is why many times, if you have ever tried to do this, with your brother or your sister or your friend while playing, you would find it quite difficult to do because usually we are not trained for this position. We usually try to just grab someone while they're still standing straight. Let's do another sample problem. Now, I know rotation is slightly more difficult than translational motion because we usually don't experience rotation on a daily basis, normal things like we do with translation. So we'll do a couple examples on it. Take a look at this system. We have a uniform disk with some mass, 2.5 kilograms. So previously, we used to ignore any mass of these pulleys. We always said, ignore the whole mass thing. But that's not realistic. In real life, if I have a pulley, if I have a gear, if I have a rotating thingy, there is mass on it. So I need to take that into consideration. So we have here a uniform disk with a mass 2.5 kilos and a radius 20 centimeters, mounted on a fixed horizontal axis. I have a block with mass 1.2 kilograms that is hanging from a massless cord, and we can say cord is massless because it's going to be a few grams at max. Okay, which is wrapped around the rim of the disk. Find the acceleration of the falling block, the angular acceleration of the disk, and the tension in the cord. The cord does not slip and there's no friction at the axle. Now, previously, we would simply say, okay, force down mg, force up tension, there's nothing holding it from the top, خلصنا. But now we actually have this mass on the axle, on the rotating thing. Things will slightly be more complicated. Sorry, just a second. Okay, let's start. We have the mass of the rotating disc is 2.5 kilos. Mass of the block is 1.2 kilos. Radius of the rotating disc is 20 centimeters. From our list in the book, we know the moment of inertia of a solid disk is half mr squared. We want to know the tension, we want to know the acceleration linearly of the massive block, and the angular acceleration of the rotating disk. Free body diagram, we have gravity downwards, tension upwards, just like before. So looking at just the forces, just like before, we have T minus mg equals ma in the negative direction, so minus ma. So far, so good. We're not doing anything new. It's the same as before. But now, since this thing has a mass, we need to also consider that when this rope is pulling down on this thing, when the rope is pulling down on this thing, it is also exerting a torque. Okay, so if you think of terms of energy, there is a bit of energy going into making this heavy rotating thing actually rotate. So my torque net is R cross F, so R times minus T, is equal to I alpha. So this is R cross F. This is I, and well, this is alpha. So you have two equations. Okay, one with forces, one with torques. Now we can combine equation 1 and equation 2 to end up knowing that T equals half ma, acceleration equals g2m over m plus 2m, and alpha equals a over r. Okay, so we have more than one unknown. We need more than one equation. We have one equation with the force. We have another equation with the torque. Any questions so far?
Mister, can you repeat this part?
Which part?
Final part.
So we have two equations, one with only the forces, one with the torques. Now we need to combine these two equations to get our unknowns. So we need T, A, and alpha. Let's see what we can get. What other equations can we use? We can use A tangential equals alpha r. So from 1, we can do T minus mg equals m minus a, which is equal to m minus alpha r, just from here. I'll copy the final results and then we can go through them one by one. So let's see. We want to know what is tension to start with. Yeah? Okay. First thing first, the easiest thing to find is alpha. It's A over R by definition from this equation. So alpha equals A over R. This is easy. Now, of course, the problem is we don't really know what A is. So, this is not the most useful equation for us yet. Okay. To make it useful, we need to find what A is. Well, I can use this equation 1 inside equation 2. Okay. I have minus RT equals half mr squared minus alpha which, if I substitute this in it, will end up being half mr squared minus a over r. Now 1r here and 1r here can go away. So I end up with minus RT equals half mr this way. I have 1r here, 1r here, that can also go away. I have two minuses that can go away. And I end up with T equals half ma. I can now put it back into my equation 1. I had T minus mg equals minus ma. I have half ma minus mg equals minus ma. And if I want to have acceleration as my subject, I rearrange and I will end up with G 2m m plus 2m. Okay. So the key point here is we are no longer dealing with only forces, but also what forces cause. So forces cause a torque here. So we need to take into consideration both of them, the force and the torque. Let's think of it this way. A mass m hangs from a string wrapped around a pulley of radius r. The pulley has a moment of inertia I and its pivot is frictionless. So we don't need to deal with friction left and right. Because of gravity, the mass falls and the pulley rotates. What is the magnitude of the torque on the pulley? Is it more than mgr? Is it less than mgr? Or is it equal to mgr? That is A, B, C. And I'll give you a minute to think about it and write it down in the chat. Just write A, B, or C. Which one do you think is correct? Okay, so you have a couple of people who say less than mgr, and a couple who say equal to mgr. Okay, more answers coming in. A whole bunch of B's coming in, less than mgr. Ah, why did it stop sharing the screen? No, come back. Okay, so indeed the correct answer is less than mgr. Because just like in the previous question, okay, we have mg down, we have tension up. At this point, yeah, we have mg down, and we have this moment arm, r. So our torque is going to be I alpha, where alpha is A over R, and this is our A. So it's going to be less than mgr. Okay, because the tension on the pulley is not equal to mg. It's less than mg. Let's consider this. A mass M is attached to a long massless rod. The mass is close to one end of the rod. Is it easier to balance the rod on end with the mass near the top or near the bottom? When is it easier to balance? Easier with the mass at the top, easier with the mass at the bottom, or there's no difference? Either way, it's really easy or really difficult to balance. It's not obvious, so take your time to think about it. Okay, we have two people who said bottom. No, sorry, everyone is saying near bottom. Sluggish means slow moving. Okay, so we have about 20 odd people saying near the bottom. We have 3 people saying near the top, and 1 person saying no difference. Well, let's try it out. Okay, let the mathematics speak. We're trying to do this, and if it's too much, then it will fall down, which is a rotation. So torque is involved. Torque equals I alpha. Otherwise, I can say alpha equals torque over I. Torque equals R cross F, which is equal to R mg sine theta. In this case, the only force we have is gravity. So we end up with R mg sine theta being our torque. Now the question told us that smaller angular acceleration means it's sluggish or slow moving. Okay. Since this is a rod, my moment of inertia is equal to mr squared. plus I rod. But this thing said rod and massless, so we can ignore this bit. We're just looking at the mass of this tiny piece, mr squared. Alpha equals torque over I, which is equal to R mg sine theta divided by mr squared. R goes with one R, the M goes with M. We end up with G sine theta, which is a constant, over R. So it means it's proportional to 1 over R, which tells me that as R increases, so the further away we go from the bottom, the smaller my angular acceleration. And the smaller my angular acceleration means it's better to balance. It's easier to balance. Okay, so it's counterintuitive. By intuition, we usually go, okay, lower would probably be better. But in reality, that isn't the truth. Higher is better. Okay, so we discussed torque, we discussed force, we discussed kinetic energy, we discussed a whole bunch of things. The last one is work. We know from before that the change in kinetic energy, final minus initial kinetic energy, is equals to half mvf squared minus half mvi squared equals work done. How do we translate this to rotating? We translate, as we said before, half I omega f squared minus half I omega I squared is equal to work. Let's do an application. If we have a sphere, a hoop, and a disk, they're all rotating, and they're all with the same mass m and same radius r. Which one has the most kinetic energy? Sphere, hoop, or disk? Yes, you are correct. Hoop would have the most amount of kinetic energy. Okay, since kinetic energy is half I omega squared and it has the highest I, they all have the same radius, they all have the same mass, they all have the same linear velocity, so they have all the same. The only one, the highest one is going to be the hoop. Yes? Does anyone disagree with that? Why? Well, we said Ke equals half I omega squared. And we know from before that omega equals RV. Or was it V equals R omega? Can someone remind me?
V equals R omega.
V equals R omega? Okay. Can you see where we go from here? No? Well, since they all have the same R, since they all have the same V, this means that omega equals V over R. It's the same for all of them. So for this one, kinetic energy is going to be half I omega squared. So this will be mr squared omega squared over 5. This will be also half I omega squared. And this would simply be mr squared omega squared over 2. And this would be half I omega squared, which is mr squared omega squared over 4. And out of these three, this one has the highest kinetic energy. As usual, when we look at work, we used to integrate f dx from xi to xf. Now we will translate, so we'll integrate torque d theta from theta initial to theta final. If we have a fixed torque, then we end up with torque theta f minus theta final initial. If we don't have a fixed torque, then we actually need to integrate the torque with respect to theta and see what we get. More translations. We had power equals dw by dt, so we end up with fv. Now we will end up with torque omega. Simple translations over and over and over again. Okay. Now we have done things that move in straight lines, translational motion or linear motion. And we have done things that rotate while being fixed in place. Pure rotation, it's moving in its place. Pure translation, moving from A to B but without rotating. The natural progression is, what about this? Like a wheel or a football. It's rotating and it's going from point A to point B at the same time. How do we deal with this motion? First thing first, we give it a name and we call it rolling motion. Okay, it's rolling. There is rotation and there is translation. Now, if I want to trace what happens, the center of it while it's moving is going in a straight line. But if I trace an actual point on the edge, I will have multiple arcs. If I want to specify how is it moving in the XY direction, not rotation, I will describe it using its VCOM. Okay. Let's start getting weird. I'm looking at the center of this thing. Okay. And it is going from this point to that point. What is its velocity of the center of mass? Distance over time, right? Distance S over time T, S over T. هل في اعتراض؟ No? Good. Okay. Let's do the same thing, same calculation, but for another point. This point down here. This point down here. In the same amount of time t, how much has it moved? Well, it has moved, it has gone up from here all the way to this point up here. So it has moved theta r. Yeah? Okay. Here's where the weird starts. If I look at the center of the wheel, my VCOM doesn't really change. Okay. Actually, let's do it a different way. We said that rolling is rotation plus translation. So let's look at what we have in rotation, what we have in translation, and see what we get. In rotation, in pure rotation, the center does not move, so the velocity here is 0. The top moves VCOM to the right. The bottom moves minus VCOM to the left. Okay. Let's look at pure translation. Well, everything's moving in the same direction with the same velocity, VCOM. But what when we have both of them together and rolling? Let's add them up. At the top, we have 2 VCOM. At the middle, we have VCOM. And at the bottom, we have 0. Which is really, really weird. I'm saying that one object, one wheel, has 3 different velocities. Does this make sense to you?
No.
Yet, the mathematics seem to prove it. Let's see what is the effect of this in real life. Do we have any photography fans here? People who like to photograph things?
Yes, doctor.
Okay, so if you're into photography, you know how to use one of these, and you know you can play around with the shutter time, right? You know you can play around with the shutter time to be as, low as 1 over, 64,000, 1 over 12,800. And you can go all the way up to having your shutter open for, half a minute, or if you're into really, really a lot of, long-term photography, then you can go up to a few minutes or time lapses. Actually, time lapse is a different thing, never mind. But, really long shutter speeds. Like you can keep your lens open for 30 seconds, 1 minute, etc. Now, here's what happens. And you might have noticed this before in some of your photographs, but you never understood why. Say someone is moving their head left and right, and you take a photograph, yeah, and you set your shutter speed to something reasonable. This is what you see, right? Okay. Fine. Now, you have moving photography where stuff is moving. You have some really, really fancy lenses, okay, to correct all sorts of aberrations. You can go as big as this, okay. But you will end up with a photo like this, no matter how good the lens is. Have you ever taken a photo of a rolling object and ended up with something like this? It seems as if there are 3 different focus points in one photograph. You have this region, which is absolutely perfectly in focus. You have this region, which is nos. And then you have this region, which is really, really bad and out of focus. Now, you as the photographer, you swear that you set the focus correctly. You swear that you have tried out every single possible shutter combination, and you still end up with something like this. Then you try doing something. You try fixing it somehow. Okay, you try increasing the shutter time or decreasing the shutter time. You really want to focus this area. You really, really, really want to focus this area up top. But now when you focus up here, this area goes out of focus. Ever gone through this problem? And it doesn't matter what you do, you're unable to fix it. The reason for that is, let's analyze the motion of the wheels. Each point of it is moving, right, in a certain direction. But V top, now you are rotating on this point, right? You're rolling, this point is fixed. Yeah, this is fixed. At the top, you have omega 2r, the rotation speed is fixed, but you are 2r away, so r, 2r, omega 2r, 2 omega r. And the center, what is your V though? Velocity. Omega r. What is the problem? And what is your velocity at the very bottom? Linear velocity, not rotational. That point is fixed on the ground. Your velocity there is 0, linear velocity. So the problem is not with you not being able to focus your image properly or setting the shutter time properly. The problem is in the physics, because this one stupid object seems to have 3 different linear velocities on the same object. So you are only able to get it properly fixed in one of these 3 locations. You set your shutter time, your exposure time, etc., and you're only able to focus it on one of these regions because they actually have 3 different velocities. Yes, that is very normal, Lubna, actually. It took me a very long time to get my head around this. And I think a very, very key point to remembering this actually is I think a very, very key point to understanding this is, do I have this here? Nope, not here. Where did that thing go? I had a presentation here. Okay. Okay, I seem to have lost that presentation. There we go. So if you remember from our lecture some time ago, we had this. Do you remember this? This is the key point to what happens now on the wheel and this headache. Okay. Now here what you have is the same rotational velocity gives you different linear velocities for two different people on the same object. Yeah. Do you remember this bit? How do I... Do you remember this bit? Yeah. Look at the speed that now we are sure they are on the same line. So they take the same amount of time to go through the circle. This is a fact. But look at their velocities independently. You can see from the photo, from this GIF, that the red one is moving at a faster speed than the blue one. Now, usually, if you see this on a post on Facebook, it would probably say something like, this is an illusion, خداع بصري. Yeah, but this is not your eyes playing a trick on you. Yeah, to go through the same 360 degrees at the same time, one of them needs to have a higher velocity than the other one. Yeah. And if we understand this concept, okay, as difficult as it is, if we understand this concept to a certain extent, we can start understanding this. Okay, because we have different velocities for different objects, for different regions of the same object. This is the key point here. And I think conceptually, out of all of chapter 10, this might be the most difficult thing to get your head around conceptually. Yeah, how the same object can have 3 different velocities at 3 different speeds. So if I take this point A, point B, point C, point D, point E, point F, point G, point H, point I, and if I ask for what is their alpha, all their alphas are equal. Yeah. If I ask for their omegas, they're all the same. They go through 360 degrees at the exact same rate. But if I ask for their linear velocity component, translational component, yeah, the velocity of center of mass, for example, or just the velocity at that point, yeah, how fast is this thing rotating going in this direction? You get 3 different velocities. Yeah. The reason here it's at 0 at the bottom is because these 2 locations, pretty much this location, if you look at it, it's fixed on the ground. So it looks as if it doesn't move. It sounds stupid. It sounds illogical. It's difficult to get our heads around. But at the end of the day, this is a photo. This is not a CGI computer rendering. And if you are a photographer, if you have ever tried taking a photo of something rotating fast enough, you will have faced this problem. Yeah. If you have a bicycle, if you're a little brother, little sister at home, go outside, take a photo of it. You will see this is true. If you're bored, lie down on the floor, take a photo of the ceiling fan. You will see something similar. Now, of course, for the ceiling fan, it will be slightly different because that is rotate. Actually, that's rotating, not rolling. It's not going anywhere. Okay. Let's do one last PIQ before we call it a day. A circular hoop rolls without slipping on a flat horizontal surface. Which one of the following must be true? A, all points on the rim of the hoop have the same speed. B, all points on the rim of the hoop have the same velocity. Or C, every point on the rim of the wheel has a different velocity. You have 2 minutes. Think about it slowly, then type your answer in the chat. Yep. Pretty much everyone has chosen the correct answer. Oops. Pretty much everyone has chosen the correct answer, C. Every point on the rim of the wheel has a different velocity. Cool. So this is it for today. Our lecture time is over, and we have covered all the material that we need to be covering. See you, inshallah, on Wednesday, continuing with chapter 11.
Doctor, what about the quiz?